Hello everyone, this is Ran. I am from the University of Minnesota Twin Cities, and today I would like to introduce our paperwork for the workshop, which is related with virtual human simulation in crowd simulation. So this is a work in progress paper, and in this study, we are trying to add head rotation animation into virtual humans, especially in some scenarios where there may be collision avoidance happen, and also we hope that this head rotation animation could improve the realism of the virtual human simulation. So the first, I would like to introduce some motivations of our study. Before a while ago, we did some experiments with in VR with interaction between real human and virtual humans. In these experiments, we control these virtual humans by several different kinds of crowd simulation algorithms. For example, some algorithms are based on is force based, some are experiment based, some algorithms are data driven based. So in these experiments, we design some scenarios where there may be collision happen, and we ask the user to wear head-mount display to interact with these virtual humans. We have the user to try these similar scenarios with different algorithm-controlled virtual humans, and ask the user how realism of these virtual humans perform, and also what's different between these algorithms. So here is here is a video which shows the experiments we did at that time. So as you can see, two virtual humans walk towards me, and there may be collision happens, right? So as you can see, they can avoid the collision. Very smart. But if you notice that we didn't add any other animations to these virtual humans, like gaze or head rotation or even like gestures. So from this experiment, we get some feedback from the user, in which they said that they still feel that although these virtual humans could avoid collisions, but their movement and their response are not as realism as they expect. Especially that these virtual humans never notice that the user exists, right? So after these experiments, we come up with some ideas that to improve the realism of the virtual human simulation by talking about improvement. We are not talking about the collision avoidance algorithm. We are talking about adding more other factors which could help us to improve it. For example, so we did some research work. For example, usually if we add some visual attention behavior or gaze behavior, the realism of the simulation could be improved in some scenarios like conversation scenarios and conversational scenarios, and also like walking interaction. Also, some body move and gestures could happen if you are like very close to each other. And also some psychology factors like the personal space or some fear emotion could also like make the virtual human like a real human being. There is one thing we don't find is head rotation. So we think this drives us to do some study work on adding the head rotation onto these virtual humans, and especially in these collision avoidance scenarios. So our target for this study is to improve the realism of virtual human simulation and also add head rotation, which means to add head rotation to crowd simulation in our specific case, and especially in collision avoidance. So, in order to add these head rotations, we need to figure out how collision avoidance happens. So we know that in our daily walking, we don't collide a lot with the other guys, right? So that's because we could predict some future collisions and change our directions immediately before we collide with the others, right? So we call it as future collision prediction. These future collisions is based on the current state. And for real human, they usually would predict the collision first, and immediately after they notice that there may be some collision happen, immediately they would adjust their direction or speed or do some turn their head, right? So this is what humans do. They turn their head. The head turning may happen in these collision situations. So why they do that? Because they want to get a better view and to signal the others, right? So after this kind of analysis, we come up with an assumption for our like head turning strategies, which is when humans notice or predict some future possible collisions, they might turn their heads to get a better view or to give a signal to the other pedestrians. So in this assumption, we explain two things. The first is in which kind of situations people may turn their head. The second thing is why they turn their head, right? So for when people turn their head, when there may be a collision happen. So for why? Because they want to get a better view to see the other pedestrian better, or they would like to signal the other pedestrians to let them know that, okay, I noticed you, I would slow down or speed up, so I don't want to collide with you. Okay, so based on this assumption, we would like to figure out when will this happen in an accurate in an accurate way. So we find one important thing we find which may be helpful are some metrics which could help us to predict these future possible collisions. There are two metrics which could predict these future collisions efficiently. The first one is time to collision. The second one is minimum predicted distance. You can tell the meaning of these two metrics from their names. I will talk about them more specifically in later. But as you can see, time to collision is to compute the time you may take, how long a time to collision is a metric which could tell you that how many seconds after how many seconds the collision may happen if you keep the current speed and velocity. And for the minimum predicted distance, it is if you keep your current state, how close you may get from to the other agent, right? This is how this metric stands for. Okay, so if we have these two metrics, which could tell us when the collision may happen or whether it will happen, then we can determine that which conditions these virtual humans could turn their head. So which means that the usage of these metrics are involving these metrics to find high possibility of future collision states, right? Okay, so let's talk about these two metrics. The first one is timed collision. Here is an equation for calculating the time to collision, which we call it as TTC. TTC is formally raised in a paper written by Ioannis and Ioannis, which is a paper introduce a cross avoidance, cross simulation algorithm based on energy and time to collision. So we only use the TTC metric from that paper here. So in this equation, you can say P is the position, V is the velocity, and R is the radian. So this equation, A and B are the two agents, and P plus velocity times time times T would be the position or the distance of the from this equation we can see that if we solve this equation, we know the T would be the time when the collision happens, right? So for this, this is a quadratic equation, and if the only thing we don't know for this equation is T. So if this equation if T has a non-negative solution result exists, then the collision may happen in the future if the agents keep the current velocities. If there is no solution exists, then no collision will happen. So using this metric, the TTC, the result of this equation for T, we know that if the timed collision is very short, is below than a threshold, then it means that two agents may collide in a very future short time. So we ask the virtual human to turn their head at this time. So which means that if TTC is smaller than a threshold tau, then we will add head rotation on the virtual human. And we will have the virtual human turn his or her head back when TTC goes back above the threshold top. Okay, for the next metric, which is minimum predicted distance, we call it MPD, we also have an equation. It's very similar like the TTC. This equation calculates the minimum distance between these two agents. So P is still the position, V is the velocity, and T is for each time step. Okay, for each time step, we have a future time, which is U, and for each time step T, there will exist future time U, in which state the two agents will be the closest to each other ever. So using this metric, MPD, we say that if the MPD is lower than a threshold, which means that the two agents may get very, very close. Like, for example, D is 1 meter, is 1. Then if the two agents get may be two agents may be only 1 meter from each other, we see that it would be very uncomfortable for the real human. And we hope, in this situation, we add the head turning animation to the virtual human if the MPD between these two users is smaller than a threshold. So on the in this slide, we put a figure which we took from the paper, which introduced this metric from the Professor Julian. In that paper, they used MPD as a way to measure how two agents interact with each other. And as you can see that they use the MPD to separate the interaction into 3 different phases. If the MPD is very low, they call it as observation time period. And after the observation period, humans will adjust their velocity and to avoid the collision. So the MPD will goes up in the following phase, which is called reaction time period. And then the two agents may avoid collision successfully. Okay, after introducing the two metrics and our strategies to turn head, we want to set up an experiment to prove the efficiency of our assumption and to optimize the algorithm. So for the experiment setup, we have a 6 degree of freedom tracked head mount display for the real user, and ask the user, we have the user wear the head mount plate to walk in a large room, real space, and do physically walking. So here is a proposal of the experiments. As you can see, we have 2 agents. We give the 2 agents their target specifically, and we have 2 walls in the middle. This is the top view proposal. So in this experiment, we ask the user to the top one is the virtual human, and the above one, the top circle is the virtual human. The above circle, the bottom circle is the real user. The top circle is the virtual human. So we use our head turning strategy on this virtual human, and well, at the same time, this virtual human is controlled by a crowd simulation algorithm, which is called ORCA. And we design these scenarios with like a path converge thing, where the user can, in this interaction in the middle, the user could choose to give way to the virtual human or to pass it if they prefer. Anyway, we ask them to go to their target as smooth as possible and avoid collision. So for the real human, they will wear the head-mount display and walk to their target, which we marked as a pillar, and we ask them to try to avoid collisions with the virtual human. So basically, we will have the real human and the virtual human start to walk at the same time, so they can see each other in the middle of the area. So here are some benefits of this design. The first is that in this scenario, there are high possibilities for collision happens in the interaction. And also, the second is, as you can see, there are two walls in the middle, which could help us to block the early view for both the two agents. So they can, we ask them to respond in a very short time, not at the very beginning. Because for the third point, as you can see, head rotation usually happens when users try to solve the collision dilemma in a very short time. If they are too far away from each other, then the head rotation may not be necessary to get a better view or to signal each other, right? Because if you are too far away, you cannot see some head rotation very clearly. Another thing we need to, I like to point out is the target position. As you can see, we don't set the target position in the corner of this square. We put it in the middle top middle position as the target of the real user. We do this because the real user who wears the head-mount display may have a field of view limitation, which is not as wide as in the real world. So if we put the target in the right corner, right up corner, the real human may not be able to even notice the virtual human, right? So we adjust the position of the user's target, and so make sure that the real human could notice the virtual human and even see his or her head rotation very clearly. So here is a screenshot of the experiment design. On the left side, it is a user who wears the head-mount display and walk in our experiment room. On the right side is the virtual world, which have the same size as the real world. You can see the virtual character Mia turn her head while interacting with the real user. Here is a video which shows here is a video which shows some comparison, some result shows shows the simulation of our shows the result of the simulation using that experiment proposal. As you can see, you have two walls and a pillar target for the real user, and the virtual human walked from the other side. So as you can see, this is without head rotation for the virtual human. This is with the head rotation. And still no head rotation. And with head rotation, will the virtual human pass first? So as you can see, if we add the head rotation to the virtual human will give you some signal that she noticed you and would like to avoid collision with you, right? And in this case, this is we have some same, like we could see that the virtual human noticed you and take a look at you, see that you slowed down, and then she turned her head back and walked straight to pass first. Okay. So from the feedback of our users, we got some initial findings where the users say that add head rotation do improve the realism of this virtual human simulation, especially that in the when they're trying to avoid collision, the virtual human could notice that I slow down or I want to pass first. So we would say that these are some very good starts, and yeah, and for this demo, we use the metric MPD and set the threshold as 1. So which means that when MPD is below lower than 1, then the virtual human will turn her head. If it gets higher, it gets higher back higher than 1, then she will turn her head back. Okay, so although we only did some initial experiments, we have some future plans for what we will do next. So the first, we will try different thresholds for with the metrics and see which threshold may be better. And also, we would like to optimize these head turning durations and angles to avoid some situations where the virtual humans turn their head very quickly or for a very long time, which we consider as a very weird behavior. And also, we may try that to only turn the virtual human's head for a little bit while and then turn head back quickly, even though it's still behind the below than the threshold. So we would also like to track the real user's head rotation behavior during the interaction and maybe try more scenarios. Yes, please let me know if you have any questions. Thanks very much.